So we are looking at addition polymers. Okay. In the actual syllabus dot point we're looking at, it says to model and compare the structure, properties, and uses of addition polymers of ethylene. So I think, Luke, you were saying the other day, what's the common name of polyethylene? There you go. All right, and then we look at the related monomers. So what we have is polyethylene, PE. We have polyvinyl chloride, PVC. We have polystyrene. Like I said, we kind of use it for styrofoam. And then we have polytetrafluoroethylene. You might know this as the common name. It's a common name called Teflon, so the frying pans. So we're going to look at these four types of polymers, look at the structure, look at what type of properties they have, and then where are they being used. Okay. So the first thing we can start off with, I shouldn't say properties of alkenes, alkynes, I forgot to change that. But what you can see here is the different types of plastics that you have. Now remember, synthetic polymers, the most common application is plastic, or plastic is polymers. Okay, so we range it from different types. We actually have two different types of polyethylene. We have low density polyethylene and then high density polyethylene. And you can actually see where each one can be used. So if it's a low density, we have cleaning bags, newspaper bags. Basically for really flexible plastic, it's low density. For the more hard, rigid plastics, such as, bottle containers, detergent bottles, shampoo bottles, higher density there. So we're going to first do a comparison between what is high density and low density polyethylene, and then we'll go into the other ones that we talked about in that syllabus dot point. Okay, now in terms of formation of polymers, the actual process that we're talking about is, like I said, addition polymerization. So the way this one works, as you can see here, we have our basic monomer, and this monomer is going to break its double bond apart. It's going to break that double bond into a single bond, and it will give additional electron density to one of the sides, and that's going to attack another monomer that's adjacent to it of the same kind. Now, one of the things we need to explain is how does addition polymerization actually work. It requires a couple of conditions. You might want to use a catalyst, or just having really high pressure and high temperature conditions. Okay. This is a little animation that kind of shows the procedure. There's 3 steps in total. You can see the first step says a free radical. So that's actually step 1. Okay. You can also see that depending on the type of polymer we generate, they might be easier to recycle. Others might not be as easy to recycle, and that's all based down to their chemical structure. Okay. So the first thing we have in the comparisons is a low density polyethylene and high density polyethylene. Now if you actually look at the overall structure of the two, you can actually see the high density one, we have a longer carbon chain and less of this concept of branch stacking. Whereas with the low density one, we have a lot more branch stacking along the main chain. Okay. Now the reason why there is a structural difference, so it's made out of the same monomer. It's still made out of ethene. That's the monomer. But it's the conditions under which these two are formed that separates their structural structure. If it's a low density, we undertake a high temperature and high pressure system. The exact numbers we use, it's written on the other slide, but I'll just write it down here as well. For high temperature, we're talking about 300 degrees Celsius high. And for pressure, we're talking about 300 atmospheric megapascals, around that kind of pressure there. So the reason why that would lead to a lot of stacking is obviously there's a lot of movement going on, and that's creating the additional stacking of these kind of things. We will talk about what these branches are, but to put it simply, the actual branches that you will see is just the alkyl groups, okay, or what you can imagine as sort of the CH3 functional group being added on to the main chain. High density polymers or polyethylene, they don't have this stacking. The main reason being is because they actually use a catalyst. And as you know, a catalyst will help bind different branches together, so it puts the orientation correctly. So if we have the correct orientation, we don't need as much energy to cause the reaction to occur. So hence, we can use it at a lower temperature. Because we're using it at a lower temperature as well, we have less branch stacking as we see, and then you can see that it's kind of more tightly packed together. So if we're talking about density here, the high density, well, given in the name, the reason why it's high density is because there's not as much stacking, whereas low density, the reason why it's not as dense is because there's a lot more stacking apart. Okay, if you want to try and imagine how we can work that out, imagine we draw a second sort of chain next to it. So if I try and draw a second high density polymer ethyl chain, because these branches aren't that wide or aren't as frequent, these two polymers can come close together in comparison to if it was a low density one where the stacking of the branches will actually push it away from each other. So that's kind of what we're having there. Okay, so got that. I will move on because obviously, like I said, this is recorded, so you can always watch it at your own pace once we're done. Okay, so if we actually look at the different stages of the production of the low density polyethylene, we have three parts. We have initiation, propagation, and termination. Now in the syllabus it's not... Oh yes, I'll answer that in a second, okay? Thank you, Owen. So initiation, as you can see here, we have R. If you remember, the actual symbol for R is the alkyl group. So we have a free radical alkyl group. So let's say CH3, free alkyl group, and it's going to try and interact with this carbon here. Okay, in response, the double bond breaks. Okay, that causes a generation of a free radical to this carbon on the adjacent side. So this is the initiation step. This is the thing that's going to cause the monomer to then latch on to other monomers. So that's the initiation, what we're talking about there. If we don't have this free radical to kickstart it, it won't start. The next one we have is propagation. So propagation is where now we have this free radical monomer. It's going to also try and latch on to an adjacent monomer, and it's going to continue doing the same process. Okay, so it's a repetition of what we did here. That's propagation. The final step we have is termination. So if you have a look at these two reactants here, there's a slight difference with this chemical compared to the ones we were showing before. This one is a saturated hydrocarbon, sorry. So it's saturated. We don't have any double bonds. These are all single bonds. It's latched onto an alkyl group here, which means when these two combine to form a bond, okay, they're not going to be able to then create another additional free radical that can then latch on to another monomer. So that basically ends the chain building for our polymer here. Okay, so these are the three steps. One of the homework questions I'll put through is going to ask you about these 3 steps, so it's nice to sort of practice through all that as well. Okay, so this kind of gives you a little intro of how the 3 steps work. Initiation, when you put a chemical in, that acts like an intermediate to cause linkage with the monomers. Now, this chemical we use, because it is reacting with the monomer, it's not a catalyst, okay? So that's kind of the difference we're saying here. Because it actually reacts with our chemicals, it's not a catalyst. We have propagation, so the activated monomer, the monomer that's become a free radical, will continue to react with other ethene monomers to increase the chain length, until a certain point where we connect to another chain that cannot form an additional bond, so they could be just saturated hydrocarbons. Then the chain terminates and we have a non-activated species. Okay, so that's how we form the low density polyethylene. In terms of the production of the high density one, like we said, because we're using a catalyst, the actual density, the actual pressure required to generate it is very low. So 1 to 2 atmospheric pressure. If you recall, 1 atmospheric pressure is the one we're experiencing right now. 60 degrees, most people have their cup of tea around 60 degrees. So it's a very low temperature there. So in this process, we're using this particular catalyst here, and that reduces the amount of stacking. Okay, so that's what we have here. And because there's a lack of stacking or branching, you can put these branches really close to each other, and hence the name high density. Okay, so there's the 2 structures. Okay, high density, low density there. Next, we're going to try and look at how does their structure influence how they're being used. Okay, so with the low density, obviously low density, because it has a low density as well, the dispersion forces are very weak, because the branches are very far away from each other, so there's not a lot of strong interaction between polymers. Okay, because it has a really weak dispersion force, you'll find that these type of plastics will be really flexible. Okay, so the plastic bags that you use when you go grocery shopping or chemist warehouse, anything like that, they're using low density polyethylene. The main function is because it is quite flexible. The high density one, because the polymers are a lot much closer packed together, they're going to have a much stronger dispersion force, which also means if it has a stronger dispersion force, we are seeing a less flexible plastic, and it also has a higher melting point. So that's why with containers, they're a lot more rigid. Okay, they can't really be bent that easily. Another way of saying if it's not flexible, we can call it just rigid. And so that's what we're dealing with here. And that all has to do with the fact that it's high in density. Okay. Another thing you might also want to mention is that this particular monomer only has dispersion forces only, no dipole, no hydrogen bonding, as the structure only has carbon and hydrogen with it. Okay, so that's what we have there. Alright, I'll just give you a bit of time to copy. So I'm saying with the polyethylene, they only have dispersion forces. They don't have dipole or hydrogen intermolecular bonds, obviously because of the structure only has carbon and hydrogen in it. No worries. Okay. So let's actually look at the uses. Now I kind of already discussed before. The low density polyethylene is going to be used for highly flexible plastics, whereas the high density polyethylenes are going to be used for highly rigid, very inflexible plastics that we have here. Okay, so you could be for buckets, freezers, anything you want to try and hold something that might be easily moving about. Okay, so that's kind of what we show here. We can also comment on the structure in terms of amorphous, meaning by its disordered. So low density polyethylene, that's disordered, and the really high ordered plastics, so the ones that have really high density, we call that crystalline. Okay, so that kind of gives you a little bit of an idea. There are obviously other derivatives of ethene that we can use to make more polymers. So if we have ethene and we let it go through halogenation, so by including a halogen group, could be chlorine, and replacing it with one hydrogen group, we get vinyl chloride or chloroethene. If we substitute a benzene ring for the hydrogen, might actually even draw the structure of ethene. I know most of you know this, but it never hurts to just redraw it. So the structure of ethene is like so. So what we're trying to do with these ones is we can replace it with a different functional group. With vinyl chloride, we replace this with chlorine. With styrene, we can replace it with a benzene group instead. So it will look sort of like that attached to the double bond, yada yada yada. Okay. Alright, so if we look at the formation of polyvinyl chloride, exact same idea. It still goes through the addition, initiation, propagation, termination. What you can also see here, the monomer that we're using is vinyl chloride. The only difference, like I said, it uses chlorine, or one chlorine in that particular group. Okay. It is also amorphous, like low density polyethylene. The reason being is because, and this diagram doesn't really show it very well, chlorine is a much bigger atom than hydrogen and carbon. Okay, so you can think of, if you try and picture the formation of this polymer, when it's creating its actual chain, this is one big sort of element that's sort of there. So the fact that it's really big, it makes it really difficult to sort of build the chain around a long chain, because you have this really big atom blocking everything. Okay, so due to this large size, it really sticks out in the chain, and so that makes it a very disordered type of chain structure. But unlike the low density polyethylene, it tends to be more hard and rigid, polyvinyl chloride. The other thing that it has that's slightly different is it has a polar bond. Okay, so between the carbon and chloride bond, we have dipole-dipole interactions. So that's kind of the reason why it's more hard and more rigid. Because of this dipole-dipole bond, it creates a stronger bond between the different or the same polymers. Okay, so that's why even though it has low density, it's still hard and rigid because it has a stronger interaction of the intermolecular forces. Okay, so I'll let you just quickly jot that down. So let's just continue on. So in terms of applications, you can actually see these are very rigid structures, rigid type of plastics that we have. Okay, so if we actually decrease the type of dispersion forces between the PVC, we get these kind of nice little tubes that are a little bit more flexible. We can restructure it to be UV light absorbers, so to block out any UV light coming through. And we could also use it for heat stabilizers because of this additional dipole-dipole interaction. It means that the melting point of the plastic is a lot higher, so it can be used as a way of, stabilizing heat in any pipe work or any flammable object that you're using. So it's quite useful there. Okay, so those are the applications we have with PVC. All right, move along. All right, so we talked about PVC. Next, we're going to actually look at styrene. And like we said a couple of times, styrene, you would have known this, styrofoam, same idea. As you could imagine, this kind of picture kind of presents it a bit nicer for you. It has a benzene ring in it. So it's made from styrene, the monomer. You could also call it by its actual scientific name, ethyl benzene monomers. You can actually see in this actual monomer, the major issue with why it's disordered is because of this benzene ring. Now this picture again doesn't quite show you how big it is, but benzene is made up of 6 carbons here. 6 carbons and 5 hydrogens. The hydrogens, that's a different story, but this is a really big ring, okay? So it means when you're constructing the actual polymer, there's a lot of stacking or branching that's going to occur because of that. And so it's going to be very low in density due to this benzene ring that we have here. Okay, so what that means is it's going to restrict the type of polymer we can create. So with that restriction, again, you're going to be separating that. Because of that restriction, this polymer is going to be quite brittle and quite hard. The other thing that's going to dictate is it's non-polar. Okay, the way we can kind of work it out is benzene. All right, if you kind of look at each direction it's in, benzene is quite symmetric. Okay, we always said that if it's a symmetric compound or molecule, it won't be polar. Okay, it'll be non-polar. So that's why it's kind of hard and brittle, relating back to the intermolecular forces. Okay, so I guess the common theme that we're trying to show here is if you're trying to show how do the structures of each of these polymers differ, you need to comment on the type of intermolecular forces, and obviously you need to remember the actual structures. So how you draw the different structures of the other ones, or at least know the monomers that make these polymers. Okay, that would be quite crucial. Okay, so moving along. If we're looking at applications, so like I said, styrofoam is an example of polystyrene applications. So it's quite useful there. We also have crystal polystyrene, so a clear polymer that exhibits high stiffness and excellent electrical insulation properties. So again, as you can see, for containers or storing things as well, because of its great heat and sound insulation properties. Okay, so that's our application of polystyrene there. And then the last one we haven't quite talked about is the polytetrafluoro blah 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 blah. This one here, so PTFE or Teflon. So I don't know if any one of you cook at home, but it's the same sort of material they use for the frying pan of Teflon. And the main difference between this monomer and the monomer we started off with is all the hydrogen bonds, all the hydrogen that's originally attached to the carbon has been replaced by fluorine. Hence the name tetrafluoro. Tetra, remember, is 4. Fluoro, fluorine. So we have 4 fluorine atoms, replacing the 4 hydrogen atoms there. And then obviously they're going to just form and create more. Yes, exactly. So it's the same material that they use to make the non-stick pads. So we can actually talk about why it's non-stick. Okay, so in terms of Teflon, it has the polar carbon fluoro bond. Now, if you remember, fluorine is the most electronegative atom on the periodic table, so that's the most electronegative. That also means that the electron difference, the difference in electronegativity, is a lot higher as well. Okay. So this is the most electronegative. Okay, and so what that allows to happen is a really strong dipole-dipole bond, or strong dipole-dipole interaction. Okay, so this makes the material really tough and strong. As a matter of fact, if we look at any solids in the world, it actually has the 3rd lowest coefficient of friction. Now, for those of you who do physics, you would understand what this means, but just to put it simply, it means that it is one of the least resistant surfaces. So you could say it's one of the smoothest surfaces you can find. In fact, when I was doing the slides, one of the factors I found was for geckos, Teflon is actually the only solid surface in the world in which they can't attach themselves onto. So that's where the non-stick stuff comes from. If the world's stickiest animal cannot stick onto it, that kind of gives you the idea of how non-stick the material is. Potentially. The reason why it is low in resistance is because of the fact that it resists the formation of dispersion forces. So if you imagine when you're trying to cook, and we always know that no matter how or any contact thing you try and do, when 2 objects contact, there is going to be some kind of dispersion force of interaction, right? Because the atoms will then try and move around, electrons, protons, they might try and interact with 2 different objects. This chemical here, or this polymer, is really good at preventing that kind of interaction from happening at all. So that's why with non-stick pans you don't see things stick, because it's preventing that bonding between the actual pan and the food from forming together. And that's the idea. Okay, so applications, obviously you have your non-stick pans. If you want to do particular joints, I think in medical industry they also use it for reconstructive. I'm not entirely sure on that one, but it is also used in the medical industry as well. Alright, so that kind of ends the explanation of the 4 different types of polymers. Just a little summary point if you need. What I would encourage you to do also is, I did upload a surfing chapter, but this morning I also re-uploaded another little bit of work that you can do. So this is actually from the 2015 HSC paper, question 25. 2 questions. One, it says, describe the steps involved in the process of addition, polymerization. So what we talked about, initiation, propagation, termination. And then question B, the most relevant part to the current syllabus dot one we just covered, is the uses of polyethylene and polystyrene in terms of their structures and properties. So I do encourage you to try and do this paper for homework. And then what we'll try and do is, if I have time tomorrow, I'll also try and see if I can give you guys feedback on your responses. So the earlier you do it, the more time I have to actually read through it and tell you how you went for that. Okay, so there's that. So I'm just going to end the recording.